Let's talk about limits with cosine and sine. So at the top of the page here, you can see the two graphs that are involved. We have y equals cosine of x, which is this wave here. Y equals sine of x is a very, very similar wave here. So without labels, these really do make the same infinite wave. The only real difference between them is that sine of x starts at the origin and cosine of x starts up high at 0, 1. But otherwise, they have the same shape. They both wave forever. So what I've shown in these graphs is like there's part of it that's a solid line and then it's dotted. So what I'm doing with the solid line is just showing like one complete cycle, 0 to 2 pi of the shape. And then essentially what the entire graph is like you make a stamp out of this shape and just keep stamping it over and over forever. So the wave continues in both directions with that shape. Same thing over here. So this solid line is just the first cycle of it. All right, so knowing that these kind of bounce between -1 and 1 forever is enough information to get by with a lot of limits. So we're going to try a few limits below, and then we'll talk about how this connects to the squeeze theorem that we learned a while ago. All right, so our first limit you can see here is just the limit as x approaches infinity of cosine of x. So we look at the cosine of x graph, and of course, x approaching infinity means the far right end behavior of this graph. And we know that it just keeps waving up and down between -1 and 1 forever. So this limit does not exist. And this is one of those, I usually call them a true DNE. It doesn't approach infinity. It doesn't go up forever. It doesn't approach negative infinity. It just kind of never settles on one y value. So this is a true DNE. Same thing for the next one, the limit of sine of x as we approach negative infinity. So on the sine of x graph and looking at the far left end behavior, but we still have that same situation where it's not going up or down forever, but it's just sort of waving up and down, never really settling into a particular y value. So this is another DNE, it does not exist. All right, so these functions can be involved in some other slightly more interesting cases here, which you can see coming up on the screen. The limit as x approaches 0 of cosine of x. This is one where you can just plug in 0. So one pleasant feature about these two graphs is they're continuous everywhere, right? No jumps, holes, vertical asymptotes, no real funny business. So if x is approaching a number, we just plug in the number, right? This is cosine of 0, which is 1. So we're talking about the y value right here in this graph. Same thing with x sine of x. So with this extra x out front here, this graph image altogether is no longer the wave. And we could kind of use some logical deduction to kind of figure out what this graph might look like, but we really don't need to know because it's the product of two continuous functions, and we can just plug in this number. So this is pi over 2 times sine of pi over 2. So that's pi over 2 times 1, and my answer is pi over 2. I never really needed to know more details about what y equals x sine of x might look like. Same thing for this last one, cosine of 1 over x squared. Because it's not just cosine of x, I don't automatically know what this whole graph looks like, but I can still figure out this limit based on my knowledge. So x is approaching infinity. So I'm going to just zoom in on part of this formula to see if I can kind of figure it out in pieces. So 1 over x squared on its own, as x approaches infinity, this goes to 0. This is a constant on top over a power of x on the bottom. As x gets really large, those always go to 0. So this is just going to go to whatever cosine of 0 is, which is 1. All right, so my last two examples for this video are the connection between trig limits and the squeeze theorem. And you can see the two examples here that we're going to do. They're both limits as x approach 0. That's kind of the most common setup for this style of problem. And you have an even power of x. It could be an odd power of x as well, but the even ones are more common because they keep the less thans in the right order. And then you have either sine or cosine of some expression. And what's common between these two expressions in sides, we have 1 over x here, 2 over x squared here, is that they both are the part of the formula that prevents you from plugging in this 0, right? So x approaches 0, I can't plug in 0 here. Same thing here because it causes division by 0. So both of these functions are not continuous at zero, but they both have a limit there. And it's an excellent application of the squeeze theorem. Okay, so the squeeze theorem, just as a rough refresher, is the theorem that says if your function is stuck between two other functions that have the same limit somewhere, then that must also be your function's limit. So what we want to do is say that for this first problem, x squared sine of 1 over x is between two things whose limit at 0 is both whatever, and that whatever must be my answer. Okay, so we are going to start with just the trig part of it. So here it's sine of 1 over x. And the key is that sine of absolutely any input is always between -1 and +1. And we can see that graphically here, right? They never go higher than 1 or lower than -1. And we also know that that's true from what we know about the unit circle. So sine of anything always trapped between -1 and 1. Same is true of cosine. And then what's inside the sign for this particular problem is 1 over x. So that's what I'm going to put in those empty parentheses. And just as a technicality, I'm going to write on the side for x not equal 0, only because when x equals 0, this center thing just doesn't exist at all. Okay, so this kind of starts me off so I can build up this inequality sandwich. And now what my target for this middle function is this formula here, right? So I'm missing the times x squared out front. So I'm going to multiply all three parts of this inequality sandwich by x squared so that the center is exactly my function. -1 times x squared is -x squared. In the middle, I have the x squared sine of 1 over x that I wanted. And on the right, I have x squared. So we know for every single x value except for 0, where this disappears, this function is less than this is less than that. And what's convenient now about this is that -x squared and +x squared have the same limit as x approaches 0. So we're going to compute that, right? So the limit as x approaches 0 of -x squared, this is just a plug it in continuous limit. I get -0 squared is 0. Same thing over here. 0 squared is 0. So because this function's trapped between these two and they're both headed to 0, that means my limit is also 0 by the squeeze theorem. That's kind of a really nice roadmap for how these will always work. So let's try that roadmap again with this second and final example. So I have the limit as x approaches 0 again, so same as before. And now we have x to the 4th cosine of 2 over x squared. So again, the 2 over x squared is what's stopping me from just plugging 0 into this entire formula. All right, so what I'm going to do is say, all right, cosine of anything is always trapped between -1 and 1. So this is always how we start. Cosine of absolutely anything, always between -1 and 1, can never go beyond those numbers. In this problem, what's inside cosine is 2 over x squared. So that's what I'll put here to start off. And then just to be polite, we'll mention this is, of course, for x not equal 0 because you can't plug in 0 here. Okay, but otherwise it's true. All right, and then I want to build up what I have in this middle part. So for this one, all I need to get to this function is just times x to the 4th. We'll run into, especially in the homework, some examples that have more stuff going on, right? So if this has like a times x to the 4th and like a +7, you'll do that times and then +7 to all three pieces and so on. You just keep building up until this middle is exactly the function in your limit. So for this one, we have just one step like before. That's -x to the 4th less than or equal to my target function less than or equal to +x to the 4th. Now that I have exactly my target function here, I'm going to look at those left and right side formulas and hope/expect that their limit as x approaches 0 is the same number. As long as it is, that's my final answer. And if it's not, then this isn't a valid application of the squeeze theorem. All right, so again, we compute limit as x approaches 0. This one comes out 0, so does this one. So that means this limit is also 0 by the squeeze theorem.